nim on a light switch, mostly bare metal nim on the ESP8266. Hi, my name is Christian and I'll be talking to you about my evening and weekend project to run nim on this little embedded device. My initial motivation for this project when I started in 2016 was to have a bunch of temperature sensors dotted around my house and have some nice graphs and potentially also controlling my fairly dumb room thermostats. It's mid-2020 and I still haven't achieved that. But I then found that you can buy light switches based on the ESP8266 onto which you can flash your own firmware. And this seemed like a pretty good opportunity to automate my stereo bit. My stereo is a fairly old 5.1 surround system, but I don't really see any compelling reason to get rid of it. Nevertheless, it has a very annoying feature, which is that you have to manually turn on the subwoofer. And in fact, if you want to listen to music or watch TV, then you have to get the remote and turn things on. And really, it's 2020, and I don't really expect to have to get out of my sofa for that to happen anymore. In early 2018, I bought a Sonoff S20 switch, and a few months later, I could turn the subwoofer on and off from Home Assistant, and you can do that using your phone. And that's nice, but obviously I wanted more, and at this point, the functionality of the system is quite a bit bigger, as you'll see later on. But basically, turning things on and off using Home Assistant has been what's driving all the development I'll show you. So while we're on nim on the ESP8266, well, it already runs a bunch of other things like MicroPython, Basic, Lua, Forth, JavaScript. It's got a big community. There's an Arduino port. Somebody has used nim with that. But it's clear that it's a capable platform and that it's definitely possible to run nim on it. And it's a 32-bit processor. It runs at 80 megahertz by default, but you can switch it to 160. It's got Wi-Fi, which is obviously very nice, and it's got typically 4 megabytes of flash, but up to 16. Programs are about 1 megabyte max, and you have about 50 kilobytes worth of free heap, although the SDK takes some of that for the Wi-Fi and TCP stack. There's a bunch of GPIO pins, but it's fairly modest, it's like 4 or 5, because some of the pins are used for flash and other things. And it's really, really cheap. You can get a development board with USB powered and USB to serial from a German online retailer for about 6 to 8 euros. Or you can get a module which has flash built in and an antenna for about 4 euros. There's also the ESP32, which is basically the successor to the ESP8266, and I basically consider that future work for at some point when I have time. So, why nim? Well, it basically isn't C, but it interfaces really easily with C, and that's important because we need to call into the SDK, which provides services such as connecting to Wi-Fi, networking, timers using Flash, and the SDK will also make callbacks back into nim code. Nim also has automatic memory management, which just means we won't be accessing random bits of memory accidentally. But we can deal with raw pointers and raw memory if we need to, and that's very handy when we need to call into the SDK functions. NIM's also statically typed and it has runtime checks, so even runtime errors are generally fairly graceful. It's also got powerful macros, so we can implement various abstractions and they can actually then compile to native code. Nim also has a nice syntax, that's my opinion, I think, since I write a lot of Python code in my day job, and it compiles to C, and that's really important because it means that we can just let the existing C compiler for the embedded system do all the work, and I'm not really interested in writing a compiler backend. And this also means it's fast, and so we can do things like implement interrupt service routines and do timing sensitive work without problem. Espressif does maintain a fork of LLVM with support for the ESP8266, but when I started back in 2016, this wasn't the case. But I have seen some evidence of D, Ada, and Rust using the LLVM backend, but I think mostly to target the ESP32. But I haven't really been following the progress on that very closely. We can also start it running completely without the garbage collector. This isn't really ideal. Building strings and things like that is just much easier with a garbage collector enabled. I had some success initially with the regions GC, but it seems unmaintained and there were some workarounds required. But after the introduction of ARC in 1.2, I switched to that and basically had no issues. Quite a lot of the big libraries don't actually work. They might expect to throw an exception or do other things that just don't work on embedded systems. But in general, ARC's been really good to work with. There are a couple of other components that I'll just touch briefly on that tie all of this together to make a home automation system. One is the MQTT protocol, which is a lightweight publish-subscribe message passing protocol that's specifically designed for sort of sensors and embedded devices. And I've actually got a small working prototype that implements a subset of MQTT, but enough to do real work in about 400 lines of nim. Although it's not quite done, so I'm still using a C version. And also, all of this is tied together using Home Assistant, which is an open source Python-based home automation platform, and I've got that running on a Raspberry Pi 3. And Home Assistant does the actual work by basically communicating with all my ESP-based boards using the MQTT protocol and automating by receiving messages of the states of the various sensors and devices and sending new states to other devices as required. What have I actually been doing? Well, generally I've been trying to make it easy to use nim on the ESP8266 family of devices, and I think I've probably been partially successful in that, although I don't think very many people have found the repository so far, so I think the jury's still out on that. To do that, I've wrapped the bits of the ESP8266 non-OS SDK that I need, so not everything is wrapped, and some things are probably wrapped but don't actually work. I basically lightly patch the header files before they go into C2nim, and then I have made a potentially dubious decision of extending C2nim in order to do various things that I wanted it to do, primarily so I didn't have to do any post-processing of the files by hand later. I've recently seen NimConf, which uses a slightly different approach, and that's perhaps something to look into in the future. I've also taken a lot of the code that is running on my home automation system at home and turned them into the examples that are on GitHub. And I'm trying slowly to put more examples of that from the code that I actually have. But the code that I've written is basically messy because I just want to get things to work. But yeah, I've code to send IR codes and do one-wire communication and other things, so that'd be interesting to follow. I also have an experimental macro to deal with the memory that exists on the real-time clock, which can survive a deep sleep and restart of the chip. And that basically allows us to define a data structure, and then you have basically type checking at compile time on the memory usage of that memory, even though you actually access it using function calls from the SDK. I've also built a vagrant box to try to make it easy to set up a development environment, and more recently a Docker image so that I can run continuous integration and build the SDK of that, and also build all the examples. And as always with these projects, there sadly isn't enough documentation. So let's have a look at some examples from the examples repository. One simple one and one MQTT Blinky running on this little thing. So I've got a repository with some nim on ESP8266 examples, and it's also got some instructions on how to get those built. There's also some releases with bin files and a little script to generate configurations that can be uploaded directly to a board. There are some examples in sort of increasing order of complexity. Some hello world, some obligatory LED blinking, garbage collection. The regions can probably be deleted now. Reading data from Flash, which is useful for Wi-Fi configuration and other things, as well as firmware update over there and an MQTT enabled Blinky. The Hello World SDK shows sort of a minimal example. Each example uses like a variation on the same makefile. That makefile is taken from another ESP8266 related repository and sadly has no license. So it's probably actually not the best makefile to use. And so it'd be nice to fix the builds on all of this, but that's sort of a different story. Building the nim code happens with using basically an ARM CPU that works. It's 32 bits, the right endian. No OS, no main. Compile to get some CSOL files that will then the makefile will deal with. We also generate dependencies because that's what's used to actually link all the information is used to link all the files together. The actual code, every project needs a panic override in case something should go wrong, and basically there's a little standalone file that can just output a message, and then it just feeds the watchdog timer to make sure the chip doesn't reset. What behavior you want here can obviously be adjusted to suit the project. There's a little bit of configuration for this particular example. We just turn the garbage collector off and eliminate that code, and the actual code looks fairly simple. There's just this nim user init file that uses the SDK to print the message. There's a couple of imports. The first one imports the printer function. The second one is basically from old ESP SDK versions, which needed this calibration sector set. Newer SDKs use this user pre-init, which basically sets up a little Flash partition table that the SDK can use to figure out where to read various data from. And then this file here, which basically provides a user init C function for the SDK that basically then just calls this nim user init. And if we upload and run this program, then we'll print hello world on the console. Now let's have a look at the MQTT Blinky example. It'll be running on this Node MCU board, which has got an ESP8266 on it. We'll be using a Vagrant, and there's also a Vagrant repository, which you can clone and then build a box which has all the compile tools, nim compiler and C compiler for the extensor, as well as tools to upload firmware to Flash. And it's also obviously got the nim SDK. The point of this really is to try to make things as accessible as possible, and to be able to get up and running and compile and run and flash some code onto an ESP with as little effort as possible. Not quite sure I've achieved that. It takes a very long time to build this Vagrant machine, and fairly often it doesn't actually work. So suggestions are very welcome for a better way, like a pre-built image. I'll have a look at that. Now, if everything had just worked, then we could plug in the ESP and attach it to the Vagrant box. This attached to the USB to UART bridge, so we can later upload firmware. Then we can SSH into the machine, and once we've done that, change into the directory where we've got the example stored, and for good measure we'll just make clean. And what we can do then is build some data that will, some configuration that we'll upload into Flash, and there's a little program that will actually just ask for some values and then dump those into a binary file that can later be uploaded. The data in this binary file is basically loaded from Flash into this data structure directly and then used by the program. And the data structure contains some magic, so we know what it is, the SSID, the Wi-Fi password, the MQTT IP address and port, the username and the password for the MQTT server, and last a CSC32 checksum, so we just make sure everything is good. I won't upload this file because the Flash already contains the correct configuration for my Wi-Fi network. So now we can compile the actual firmware and have a look at the board itself while we flash the firmware onto the board. And after we've done that, we'll connect to the serial port. So in a second, the board will reboot, get an IP address, and connect to the MQTT server. It's subscribed to two topics, the Blinky and then the Blinky / the MAC address, so that we can either address all of these boards or just a specific one if we had more than one running. So the top window, we're subscribing to all topics on this MQTT server, and in the bottom window we'll send some messages to this device. First, let's turn the LED on, and we can turn it off again. And you can see that we can both see the message published from the lower window and the state that's returned by the device itself. We can also set it to blink, at which point we can see the state changing on and off. So this is fundamentally what underpins the firmware and the home automation switches, basically changing the state of a GPIO pin in response to some kind of message that's published at the device. We can also just see here that it's actually printing some debug information on the serial port. Let's have a look at the code that actually drives this. So the MQTT example has much the same structure as the simple example with the makefile and user directory with the code in it. The config file is a little bit different because we now use the garbage collector, and so we define a few things for that to work, plus we define a partition to store our settings. In main.nim, we can see now that this code also uses the MQTT library, and this is a C version. Although I do have this code running with an experimental pure nim implementation of an MQTT library. The nim user looks a bit more elaborate. Basically, the first bits here load our data from Flash. Then we check if the checksum looks okay, and if it does, then we set up the Wi-Fi. And once the Wi-Fi is set up, then we call system init done to make the SDK called app init when it's ready. The Wi-Fi setup also registers a callback, so we know when we've actually got a connection to the Wi-Fi and an IP address. The app init just sets up the topics we're going to listen to, and those will be registered once we've actually got a connection. And because we now have the garbage collector, we can now just concatenate strings. So at the end of app init, we call connect, and then we wait for the registered callback to be called, which is up here. And this basically checks what kind of event we got. If we have an IP address, then we initialize the MQTT library and connect to the configured server. Then we register a non-connected callback to be able to subscribe to channels, and an on-data callback to be able to receive messages from those channels. The data callback just checks that the topic is one of the ones we're interested in, and checks the data and either turns the LED on, off, or starts the LED timer. I'll finish up the examples by showing the devices I've got running nim on at home. I've got 5 switches which control various lights and the subwoofer. Down in the corner there's a little development board which detects whether the TV is on by looking at the USB port and whether that's powered, since the TV only provides power to the USB port when it's on. The most interesting firmware is running on that board, which is a custom little board that could do with a bit of cleanup. It's basically used to detect whether the stereo is on with a little photo resistor, and also turn the stereo on using an IR diode. Additionally, it has 2 DS18B20 temperature sensors, and all this means that there is a code on this firmware to send infrared codes using the IR diode, as well as a bit banging one-wire implementation to connect to the temperature sensors. And the temperature sensors obviously produce some nice graphs, as you can see below. Thanks for watching.